we are going to derive the equation of planes. Now, this is a plane, the blue thing I drew here. If you're not sure what it is, it's a 2D surface that cuts through the 3D coordinate system. So this is like a 2D sheet of surface, and it has 0 thickness. And then it extends indefinitely to all directions. So now that you know what a plane is, what's the equation of a plane? Well, the equation of a plane depends on two things. A given normal vector, like this. I'll explain what a normal vector is later, and a given point. So the normal vector is usually represented by vector n. And let's just say it has coordinates a, b, c, or components a, b, c. The normal vector is orthogonal to the plane. Being orthogonal means being perpendicular. So vector n, you can say, is perpendicular, or more professionally, orthogonal to the plane. Okay, and we have this point here. Let's just call this green point, well, let's see, A. Now A is going to be equal to components x sub 0, y sub 0, z sub 0. These are specific numbers given in the problem. Wait, they're not components of vectors. They're coordinates. Okay, so the problem will go like this, something like this. In the 3D coordinate system, there is this plane. Vector n, the normal vector, vector n, is equal to, let's say, 3, 4, 5. And the plane also passes through point, let's say, 1, 2, 3. Now, they're going to ask you, well, what is the equation of this plane, etc., something like that. And then, basically, what we've got to do is, so firstly, we know that all equations include something like, so let's just look at equations. Equations of a line. Y equals mx plus b. We have the x component and y component to check for every coordinate. Right? We have this to check for every coordinate. For a circle, x squared plus y squared equals r squared. We have x and y to check for every component. For every, coordinate. Then, in 3D, we have the same thing, right? So essentially, in 3D equations, we have x, y, z. So essentially here, our equation should also include something like something x, something y, something z, equals whatever's on the right. So our equation needs to include these three variables, x, y, and z. So let's just call this random point g, x, y, z, and we want to verify from our equation whether or not g is a point in the plane. Now, let's just say g is on the plane. Just like imagine it's on the plane. Imagine we're just trying to derive the formula here, not exactly trying to check this. Now, g is a yellow point, okay? G is a yellow point. I'll just underline this in yellow. Then we know that from point A to the yellow point, we have a vector, right? So this vector here, vector AG, sorry, but the points should have been in like uppercase, so let me just change them. Point AG, so this is uppercase A, this is uppercase G. Vector AG is going to be equal to, well, x minus x sub 0, y minus y sub 0, and z minus z sub 0. Like that. That's our vector. And then essentially, we want this vector to be orthogonal to vector n, meaning that the vector AG and the dot product of vector AG and vector n is equal to 0. So essentially, so vector AG and vector n is equal to, the dot product of that is equal to 0 because they're orthogonal. Now what exactly is the dot product written out? Well, that's just a times x minus x sub 0 plus b times y minus y sub 0, y minus y sub 0 plus c times c minus c sub 0. And that's supposed to equal to 0. Okay, so we already have our equation because a, b, and c, x sub 0, y sub 0, and z sub 0 are specific values that will be given or will be calculated by you. If you plug those in, you get the equation with x, y, z being the only variables. So thanks